Here we go, section 6.2. We're talking about a thing called a parallelogram. Let's do, that's not us. Hang on just a sec. Okay, before we talk about a parallelogram, let's see what a normal everyday parallelogram looks like, okay? And it looks something like this. And let's scooch this up here. Let's make it a little bit bigger so we can work with it a little bit better. Okay, that's what your basic everyday normal parallelogram looks like. Now there's a couple things. Well, there's one thing you know already about this, about a parallelogram. A parallelogram is also something else that we've talked about. Look how many sides you have. What kind of a figure is that right away? Quadrilateral, right? Okay, quadrilateral. We've talked about that. What does it mean to be a quadrilateral? Four sides, okay? Just any old four, you know, as long as they're four sides and as long as they all connect and make a polygon, then it's a parallel, or it's quadrilateral. So far we only know that it's a quadrilateral, four sides. But what if I did this? What if I put a little arrow here and here? What did that say about these two sides? They're parallel to each other. And check out what word we have in the word parallelogram. You saw that right away anyway, didn't you? Okay. So it's not just these two sides are parallel. What else do you think might be true about this? The other two sides are parallel. Exactly right. So these two sides are parallel as well. And that comes, that's our definition basically. So let's write the definition down. You know I'm not a real big stickler on definitions. I don't have you write them out or anything, but I will have you write this one out though. Okay, so definition of a parallelogram. This is definition of a parallelogram. It's a quadrilateral, okay, with both pairs of sides parallel. Okay, so basically it's a quadrilateral with both pairs of sides parallel to each other. That means these two opposite sides, actually I should say both pairs of opposite sides. Let's throw that word in there. Sorry about that. Okay, with both pairs of opposite sides parallel. So these two sides are opposite and they're parallel. These two sides are opposite and they're parallel. That means we have a parallelogram. With me on that so far? Pretty easy. That's by definition. So let's do this. Let's go another color here. Here's something else. Now these things are all called theorems. We're going to write down several of them, maybe about 4 or 5 of them, something like that, 3 or 4. I forget exactly how many we have, but we'll figure it out by the end. Okay, these are all theorems. These all have to deal with a parallelogram. Now, why are the opposite sides parallel to each other? Because of the what? Definition. Now, this other stuff that we're going to show you, it's because of the theorems. They're rules. They're laws. You know, this is the rule of parallelograms. They just use this big fancy word theorem to represent that. Now it looks like they're parallel to each other, but just by looks, and I always tell you don't just go by the looks of this thing, but just looking at it, what does it look like might be true about this side and this side besides just being parallel? They're equal to each other, exactly right, and they are, all right? And there are ways to prove it. We're not going to worry about proving them. Just believe it, okay? That these two sides are parallel to each other. So if you have a parallelogram, that means these two opposite sides are equal. What do you think is true about the other two opposite sides? They're equal to each other as well. Okay? So our first theorem basically says that when you have a parallelogram, the opposite sides are equal. Okay? I'm shorthanding it, okay? Technically, you would probably have to say both pairs of opposite sides are parallel. I'm just going to say the opposite sides are parallel. We good with that? Not parallel, what? Equal, okay? They're parallel because of the definition. They're equal because of the theorem. Everybody got it? So, for instance, if I told you that this side was 5 right here, and I asked you what this bottom side was, pretty easy, isn't it? If that's 5, then that side's going to be 5. If this side was 3, then what's this side over here going to be? 3, right? You got it? Or they could do this. And you've seen this bunches and bunches of times. What if they said this was like x minus 5, and then this was 3? That's right. And then how do you solve for x? You set them equal to each other. So you go x minus 5 equals 3, and then you'd solve. What would x equal in this situation? It'd be 8, okay? Because 8 minus 5 is 3. Make sense? All right, and you can see the kind of stuff that they're going to eventually do, right? They've been doing it all year, haven't they? It's just, remember I said at the beginning of the year, each chapter isn't necessarily more difficult. It's kind of doing the same thing over and over again. It's just different figures, right? Instead of Instead of triangles, now we're messing with parallelograms. You know, we're doing the same kind of stuff. We're just doing them with different figures. That's all. So we're still in this chapter going to be setting things equal to each other. Or there'll be times where we set things supplementary, right? We add them up, set them equal to 180. The same kind of stuff we've been doing all year, we're going to be doing in this chapter as well. It's just that we're going to be doing it with different, shapes. That's basically all it is. That's what I kind of like about geometry, because if you get it from the beginning, then it's just kind of rehashing the same process throughout the whole time. Problem is, though, if you don't get it at the beginning, then each chapter is still going to be difficult, because if you can't set these two equal to each other and solve for x, then you're really going to be sunk on this chapter. But I think we're starting to get the hang of this now, so I think you'll be fine. All right, what else do we have? We got some other theorems. The opposite sides are equal. Here's something else. I'll tell you what, let's name this. And while I'm thinking about it, we actually have a little symbol for parallelogram. And guess what it looks like? Looks like a parallelogram. How about that? It's ingenious, isn't it? All right, so look, we'll call this parallelogram what? A, B, C, D. You could call it something. You could call it other things as well, couldn't you? You don't have to start with A. You could have started with B. If I wanted to start with B, what else could you call it? B what? No, you can't go B to D, though. That's the one way you can't go. You could go BA. It's not just BAD. How many vertices do you have? You got 4 vertices. You could go BADC, right? Or you could go what? BCDA. I could have called this something else starting with A. Instead of going ABCD this way, I could have gone what? ADCB. You follow me? You just can't go across. You can't say AC, then DB or BD. You can't do that. You can go along this way, or you can go along this way. And it doesn't matter which one you start with. Everybody okay with that? All right. I just decided to make it easy and just call it ABCD, just to make it alphabetical order. Okay. So let's see. What else do they say? They say that the opposite. What else do you think? These are what? Angles. And so these two are opposite angles. What do you think is true about them? They're equal to each other, absolutely. And what do you think is probably true about B and D as well? They're equal to. All right, so, and how do we know that? Because the theorem tells us. So we have another theorem that says not the opposite sides, but the opposite what? Angles are also equal to each other. So the angles that are across from each other, not A and D, they're not opposite each other. Do you see how A is across from B? Do you see that? They're diagonal to each other. So they're opposite angles. A and C are opposite, they're equal to each other. B and D are opposite, they're equal to each other. Again, you could say that, what if I said that was 130 degrees? What would angle C be equal to then? Just 130. How do you know that? Because the opposite angles are equal on a parallelogram. Make sense? Pretty easy stuff so far, isn't it? Yeah. And it's really not going to get much more difficult than this. You just have to know the relationships between the sides and the angles. If you didn't know that the opposite angles are equal, you'd be sunk. It's just a matter of knowing what's true. All right? And again, you could do this as well. I'll give you a bigger example in a second, but again, you could just say that, like y minus 30. That thing right there is y minus 30. And so if I wanted to solve for y, what would you do? Set them equal. That's right. Y minus 30 equals 130. Do that in your head. What is it? 160. That's right. Y minus 30 equals 130. Okay, add 30 to both sides. That's 160, isn't it? So y would equal 160. Does that make sense? Okay. Now remember, these two sides right here are parallel to each other. Look at AD. Remember doing this in another chapter? Where you had two parallel lines cut by a what? What was the word? Transversal. Look at angle A. Angle A would kind of be like that angle right there. Look at angle D, though. Where would angle D be? It would be this one right here, wouldn't it? What was true about these two? We had a name for it. They're consecutive interior. Very good. And what did we say was true about consecutive interior angles? They're supplementary. They're not equal. They're supplementary. Look, they can't be equal. There's no way, because look at this. This is what kind of an angle up here? It's obtuse. What kind of an angle is this one down here? It's acute. Is there any way an obtuse could equal an acute? No, there's not. So they're not equal to each other. So don't just think everything is set equal. It's not. These are supplementary. Remember, consecutive interior angles are supplementary to each other. That means that these two add up to 180 degrees. All right, so let's throw some stuff in here. What if I said, we'll go to 130 again. All right, so we'll say it's 130. What would angle D be equal to if this was 130 up here? There's supplementary. It'd be 50. That's right. And how'd you get 50? That's it. You take 130 away from 180 and you get 50. That's easy enough, isn't it? And you know what they're going to do, don't you? They're going to put x's in there and y's in there, but you still add them up. You set them equal to 180. You have to do some algebra and solve for x and solve for y. Right? You've been doing that all year, haven't you? Yeah, so you know they're going to do that again. All right, so that's the kind of stuff they're going to do here. So what's this theorem say? It says that the consecutive interior angles are what? Supplementary, which means they add up to 180. All right, so the consecutive interior angles are supplementary. You good so far? Okay, so let's go through it one more time because we got one or two more things to talk about on this, and we'll do an example, then we'll be done. So look, what do we know by definition? By the definition, what's true about the opposite sides by definition? No, not by definition. They're parallel, right? By definition, they're parallel, because look what word we have up here. We got parallel, don't we? So the definition of the word parallelogram means the opposite sides are parallel. So by definition, the opposite sides are parallel. Now we start getting into some theorems. What does the first theorem say? The opposite sides are equal to each other. Then it says the opposite angles are equal. Then it says the consecutive interior angles are supplementary. Make sense? All right? That's not that much to remember, is it? Okay, pretty self-explanatory, I think. I mean, they kind of look like they're equal, don't they? And they are. These kind of look like they're equal to each other, and they are. Same thing with the angles. Got it? Okay, let's let me do this. Let me copy this nice parallelogram. I'm going to slide this up, and I'm going to chuck that parallelogram on here again. And let's do this. What if I connected from one corner to the other? And then I connected from this corner to this corner up here. Those lines I just made, they look like they're cutting through. We call those diagonals. So that's probably a new word for you. Okay, so if I go from one corner to another and I go through the polygon like this, we call that thing a diagonal. You know, the other class I said, I thought we had talked about diagonals, and we have talked about diagonals in here, haven't we? Yeah, we have. Watch this. I think we have talked about the word diagonals. Joe, do you remember us talking about diagonals? Yeah, because remember we did this? Remember we took a polygon and we wanted to find out how many triangles you could make out of it? Right? We went from one corner to the other. Y'all remember doing this? And then let's do this one. I probably shouldn't have picked one with so many. But there you go. Remember doing this? Yeah, and how many triangles do we have? 1, 2, 3, 4, 5, what? 6. Remember we did that n minus 2 times 180 and all that kind of stuff? So we did draw those things, and I did call them diagonals. All right, so I took those off of the YouTube, so you can't go back and look at them. But yeah, we did talk about diagonals, so that's something that should not be new to you. So we have talked about it. I don't know. You probably don't care, but that bugged me in the last class because I'm like, man, I know I talked about it. And everybody's like, nope, nope, first time I ever heard of it. But I do remember talking about them. So anyway, here's a diagonal. Now, let's see what might be true about these diagonals and what it does to this parallelogram. Now, I'm given that this is a parallelogram. All right? So this is parallelogram Abcd. So if you see this, if you see that right there, what do I know about this? Well, I know the opposite sides are parallel. I know the opposite sides are what? I already said parallel. Equal. I know the opposite angles, A and C, B and D, are what? Equal to each other. I know the consecutive interior angles are supplementary. So I know all that stuff just from that little statement right there. That tells me a whole bunch of stuff about that particular figure. Would you agree? Here's something else. Look at the diagonals. They intersect each other, obviously. What does it look like? Look at we'll call this P for point. Look at AP and CP. I mean, just eyeballing it. What does it look like might be true about that? They're congruent to each other. That's right. AP and CP, they are equal to each other. So I'm going to put a little tick mark here, a little tick mark here. All right. This is another theorem. Okay. I'm not going to prove it to you, but just believe me that they are. So if I have diagonals in a parallelogram, these two sides right here are congruent. What do you think is true about DP and BP? They're congruent to each other as well. See that? So what's the phrase? What if I have a line segment and it's cut in half? What's a word that I use a lot? It starts with a B. Bisect, that's right. So this AC is being bisected and this DB is being bisected. So guess what? Both diagonals are bisecting what? What's that? Each other. Exactly right. The diagonals are bisecting each other. So that's one of our other theorems. I'll just keep this in white. Okay, so one of our other theorems says this, is that the diagonals of a parallelogram, and I'll just do the symbol for parallelogram. That's an ugly one, but you get the idea. It's supposed to be parallelogram. The diagonals of a parallelogram bisect each other. Each other. Okay? So they bisect each other. So let's do this again. What if that was 3? What could I say about PC? Thank you. Did it take that long to figure that out, or just nobody wants to answer me? Okay. Thank you, Connor. What's AC equal to? Say it. 6. That's right. AC. If this is 3 and this is 3, then the whole thing is 6. Would you agree? All right. What about this? What if I did this? What if I said that whole thing, DB? See right there? Let's say it's 10. What could you say about a couple of these other things? What about DP? What would DP be equal to? Yeah, it's 5 because it's just split in half, right? And then what would PB be? PBB be? That would be 5 as well. You get it? Okay, so you can see what they're going to do with this. Now, they're not going to always give it to you that easy. What could they do here? They could probably say, like, this is x plus 3, and this is 5. So if this is x plus 3, what do? Set it equal to 5, and then solve for x. You with me? All right, you kind of get what they're doing here. All right, let's see. Let's do one more little thing here. Let's put, oops, I don't want that. Let's go back to my parallelogram. Let me copy this. And stick it right here. I'm going to squeeze it down just a little bit, just to make it look a little different. All right. Make it a little bit bigger. And we're going to put some stuff in here. Oh, let me pause this. I don't even have the book open. Let me get the book open. Okay, here's the example. They do have a couple diagonals in here. There's one here, and there's one right here. Let's label it first. It's QRST. And in the middle is point P. Alright, then they give you lots of stuff here. I'll tell you what, let's do a couple of these in different colors. Let's go yellow for the sides. So this side right here is 5x. This side over here is 27. Alright, let's go another color. Let's go red. Let's do the diagonals. This part of the diagonal is 2y minus 5. And this one is y plus 4. Y plus 4. Okay, we're getting there. Let's go green here. Let's say this is 95 degrees up here. This one is 33 degrees. And this one down here is 3z degrees. That's a 3z, not a 33. It's a 3z. Abby? Which one? This one? Y plus 4. And I think I covered everything. Yep. So, look at the variables we have. We have x, we have y, and we have z, don't we? So let's do the x first. So let's take a look at this x right here. There's the 5x. What else are we going to use with that? We're not going to use the angles, are we? What are we going to use? The 27, right, because look, the opposite sides are equal to each other, aren't they? So 5x equals 27. So let's write that down. So 5x equals 27. Divide both sides by 5, and that's your answer. I would just keep it like that. I would just keep it 27 over 5. I mean, if you put it into a calculator, got a decimal, I guess that would be okay. I would still give it to you. But if it was me, I would just keep it 27 over 5. I wouldn't put it in the calculator, because what can you make? What can you do You can make a mistake, that's right, by punching numbers into a calculator. I mean, it doesn't happen often, but has anybody ever made a mistake punching a number into a calculator? I definitely have, okay? Yep. So I would just keep it like that, 27 over 5, and then you're done. That's y. Or, sorry, that's x. Y is the next one I'm getting to. Let's look at y. Look at 2y minus 5. Where's the other y? Up here, y plus 4. It's y plus 4. What can I do with those two? Set them equal to each other, because remember, this thing is bisected, isn't it? So from t to p is the same thing as from r to p. So they're equal to each other. So let's set them equal. So 2y minus 5 equals y plus 4. Subtract y from both sides. 2y minus y is y. Add a 5 to both sides. Y is 9. You okay with that? What was the geometry? The geometry was just understanding that those two segments were equal to each other, wasn't it? That's really all the geometry. The rest was just basic algebra skills. All right, let's do the z. Well, here's 3z. Wonder, is it equal to something? Is it supplementary to something? Is there any kind of relationship with anything right now? It's not really a relationship we talked about today. It is equal to 33. Give me a reason. Do you know why? Close. What is it? Alternate interior angles. Exactly right. Because what's true about QR and TS? They're what? They're parallel to each other, aren't they? Okay. Look at this thing right here. These two lines are parallel. QS is a transversal, isn't it? Everybody see that? Watch. Here's two parallel lines, and this is a transversal. So what is 3z? 3z is right here. What's the 33? It's right here. What's true about those two angles? We talked about this a few chapters ago. What's true about them? They're alternate interior angles. So what's true about alternate interior angles? They are equal to each other. So 33 and 3z are equal to each other. So we set them equal. 3z equals 33. And now we just solve for z. That's easy. Divide both sides by 3. Z is what? 11. And there you go. You got x, you got y, you got z. Notice what I did. I showed my work, didn't I? Showed my work, circled it, wrote down the relationships and all that kind of stuff, circled all three of my answers. That's what you should be doing on your homework. That's what you should do on a quiz. It's what you should do on a test. Kelly, getting all this? Okay? It's a little hard when you're looking the other way. All right, so this is the kind of stuff that you're going to be seeing on the homeworks. Sometimes it'll be more difficult than this. Sometimes it'll actually be a little easier than this, if you can imagine that. This wasn't that hard at all, I don't think. Don't you agree this is very, very, very similar to stuff we've been doing all year long? Isn't it really close to what we've been doing? Yeah, I think so. It's just a different picture. You never heard about parallelogram, but now that you learned some rules about the parallelogram, now you know what to do. Set them equal, right? All that kind of stuff. Make sense? All right. I'm going to give you a worksheet. Again, it's a front and a back, so make sure you do them both, and have fun with that.